Okay, so we said we're going to go back, and finish this Runga Kutta lab. So most of the confusion you should have is about the x's and the y's, and if in doubt, just leave them all in. But we can go a bit smarter. So I'd say we have most of this one done. Print the current, so cells int row column 1 equal to the time, cells int row column 2 equal to the temperature. That looks good. That looks good. I think that's it. Save before we run. Because it could be wrong. Forgot to put the row up. And we all make mistakes. Int row is equal to int row plus 1. That's better. And we'll look at a graph. We won't do any fancy stuff with graphs today, although we should label our graphs. Okay. T temperature maybe versus time. Okay, and we can make it more accurate with a smaller step size, but I'm quite happy with 0.1. Okay, next one, Heun's method. So we've done a lot of this. We're printing time and velocity here. So cells int row column 1 equal to dBl time. Cells int row 2 equal to dBl v. Everything here looks to be in order. Just have to put the int row up. Int row equal to int row plus 1. Yeah, so I'm just basically writing this. Look, k1 is f of v. The v is playing the role because it's dy dx, so the v is like the y. So I just have to put in the y's. So you see this y plus k1 h, and then y is equal to y plus 0.5 k1 plus 0.5 k2. Save it before we run it. This looks like quadratic air drag. There we go. Free fall with quadratic drag. Okay. Next one. So we have to do some printing. Cells int row column 1 is equal to x. Cells int row column 2 is equal to dBly. And now we're looking at, so I'm basically just going to write k3 now. So it's pretty much writing exactly this. So dBl k3 is equal to big F. What to say? So x plus h first, dBl x plus dBl h, and then y, which is y, dBl y, minus dBl k1 times dBl h plus 2 times dBl k2 times dBl h. And then dBl y is the next line. dBl y is equal to dBl y plus 1/6, 1 over 6. Don't introduce rounding error there. k1, dBl k1 plus 4 times dBl k2 plus dBl k3 times step size dBl h. So this is averaging 6 slopes. And I think we just have to put the int row by 1. And we're done. Save it before we run it. Yeah, I think if you solve it exactly, it's not too hard. Let's draw a picture in here. Here we go, y versus x. Let's keep doing that. And now we're looking at the more interesting one, the rocket. So hopefully we can get the numbers to work. So view view code, no, developer view code. So all this I think is okay. So dbl1, so we said that the derivative actually only depends on x, it doesn't depend on y at all. So I just have to do the first bits of this. So and the x is dblm, so that's k1. Oh, we need to print the current. So cells int row 1 is equal to the x, which is mass, and the other one is velocity. Now, I hope this works. This next one, so look, I just have to put the x plus h over 2. The x is m, h over 2. About k3 is big F, same thing. It's exactly the same thing. And what about dBl k4? It's, so there's a possibility that like you're not really doing runga kutta here because there's no predictors, but I won't worry about that. Sorry, m is our x, it's dBl h. Okay, and then dBl y, which is our v, is equal to dBl v plus 1/6, so it's averaging 6 slopes, dBl k1 plus 2 dBl k2. Now really we could just infer them because two of them are the same, k2 and k3, because we didn't actually do any predictors. See, k2 feeds into k3 but only in the y part of it, plus dBl, that's why we have that option explicit, dBl k4 times the step size. Hope to, I don't know if this will work now because I've written a note. I tried to fix it, but I was kind of trying to get it working on time. Save it. Variable not defined. That's why we have option explicit. Less than. Now the question is, can we make sense of this? Yeah, I think we can. So this is V versus M. But it's a really weird graph because there's no time involved and we're not used to this. So actually, this is the initial time, because that's when the mass is at its biggest, 500,000. And how the rocket works is it propels mass out the back and it uses conservation of momentum. So if you push mass out that way, you can't just have the momentum all going that way, you're going to get pushed this way. So mass that way, velocity this way. So the mass, the fuel goes out and the rocket goes the other way. And what happens then is the velocity gets really much bigger because what's happening is the rocket's actually getting lighter. And so, like if you throw out the same amount of fuel at the same speed, and now you're much lighter, your velocity is going to increase much faster. So initially there's kind of this linear behavior, but eventually it's really getting, the rocket is really getting much lighter, and so the velocity gets much larger. And I think if you solve the thing exactly, it's not difficult to solve that. I think it'll kind of go to infinity as the mass goes to zero. Now the question is mass the mass of the fuel or the mass of the rocket? It's probably the sum of both. So it probably does have a minimum. So that's what the 1000 is about. So this is actually the initial point, and the rocket gets faster and faster and faster. So can we push it a little bit further? Well, the step size is 5000, so we can't really do much further, but we can do 1, I think. No, maybe we can push it a bit more. So make the step size 500 and keep going until it's less than 500. Now maybe there might be a problem. We'll find out soon enough, I'm sure. Or maybe we'll go to less than 600. Let's just see what happens. Okay, we'll need a new graph. Because eventually in the limit, what's happening? Yeah, so what's happening in the limit is that if the mass goes to 0, think about the momentum as mass times velocity. So if mass is 0, you kind of get infinite velocity like that. And velocity is just messing around because it's a bit more complicated than that. But here you can see the velocity of the rocket getting bigger. Does it reach a maximum? You'll have to solve the equation to find out. Okay.